The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
I'm basically an engineer, and I'm working on speech recognition. And so you may wonder, so what is there to work on? Because you have a cell phone in your pocket, and you speak to it, and Siri answers you, and everything. So, and the whole thing is working in very basic principles. You start with a signal, it goes to signal processing. There is some pattern classification, of course, deep neural nets as usual, and so this recognizes the message. This recognizes what you are saying. So the question is, what is it that's, why to rock the boat? Why not keep going and try just to improve the error rates and improve the basically step by step? Because we have a good thing going. We have something which is already out there and it's working. Well, you may know the answer. So this is, imagine that you are sort of skiing or going on a sled, and suddenly you come somewhere and you have to start pushing. You don't want to do that, but you do it for the reason, because there may be another kind of slope going out there, and that's the way I feel about the speech recognition. So basically, sometimes we need to push a little bit up and maybe go slightly out of our comfort zone in order to get further. The speech is not what we are, it's not the thing which we are using for communicating with Siri. Speech is this. Basically, people speak the way I do. They hesitate. There's a lot of fillers. There's interruptions, and I don't finish the sentences. I speak with a strong accent, and so on. I become excited, and so on and so on. And we would like to put a machine there instead of the other person. Basically, this is what a speech recognition ultimately is, right? I mean, and actually, if you see what government is supporting, what the big companies are working on, this is what we are worried about. We are worried about the real speech produced by real people in the real communications by speech. And you know, I didn't mention all the disturbing things like noises and so on, but we'll get into that. So I believe that we don't only need a signal processing and information theory and machine learning, but we also need the other disciplines, and this is where you guys are coming in. So that's what I believe in. We should be working together, right? Engineering and life sciences working together. At least we should try. We should at least try to be, we engineers should be trying to inspired by life sciences. And as far as inspiration is concerned, I have the story to start with. There was a guy who won the lottery by using numbers 1, 2, 3, 6, 7, 49. And they said, well, this is, of course, unusual sequence of numbers. So they say, how did you ever get to that? He says, I'm the first child. My mother was my mother's second marriage, and my father's third marriage. And I was born on 6th of July. And of course, 6 by 7 is 49. All right? And that sometimes I feel I'm getting this sort of inspiration from you people. I may not get it right. I may not get it right, but as long as it works, I'm happy. You know, I'm not being paid of being smart and being knowledgeable about biology. I'm being really paid for making something which works. Anyways, so this is just a warm up. I saw that you will still be drinking a coffee, so I decided to start with a joke. But anyways, but it's an inspiring joke. I mean, it's about inspiration. And I will maybe point out to some of the inspiration points, which I, of course, didn't get right, but still it was working. Why do we have Audition? Josh already told us. Because we want to survive in this world. I mean, this is a little ferret or so whatever, and there is it's getting some signal, but there is an object, and ferret is worrying, is it something I should be friendly with, or it should be something which I should run away? So what is the message in this signal? Is it a danger, or is it an opportunity? Well, the same way, how do we survive in this world as human beings? So there is my wife who has some message in her head. And so she wants to tell me, eat vegetables, they are good for you. So she's using speech, and speech is actually an amazing sort of mechanism for sharing the experiences, and for actually without speech we wouldn't be where we are, I can guarantee you, because that allows us to tell the other people things what they should do without going to much trouble like a ferret with a bird. We may not have to be eaten. Maybe we just die a little bit early if we don't get this if we don't get this message. So she says this thing, and hopefully I get the message. So this is what the speech is about. But I wanted to say the speech is an important thing because it allows us to communicate abstract ideas like good for you. And that's sort of not only vegetable is thing, but a lot of abstract ideas can be conveyed by speech. And that's why I think it's kind of exciting. Why do we work on machine recognition of speech? Well, first one is, just like Edmund Hillary said, because it's there. They ask him, why did you climb Mount Everest? He said, well, because it's there. I mean, it's a challenge, right? Spoken language is one of the most amazing things I already told you before of human race. So there would be a hell if we can't build a machine which understands it. I mean, and we don't have an easy time so far yet. In addition, when you are addressing speech, you are really addressing the generic problems which we have in processing of other cognitive signals. And we touched it to some extent during this, this panel, because, you know, problems which we have in speech, we have the similar problems in perceiving images, perceiving smells. All these cognitive signals, basically, machines are not very good at it. Let's face it. Machines can add 10 billion numbers very quickly, but they cannot tell my grandmother from the monkey, right? I mean, so this is actually an important thing. Oh, there are also practical applications, obviously, access to information, voice interaction with machines, extracting information from speech data. Given how much speech is out there now, with I don't know how much we are adding every second through the YouTube and that sort of things. But there's a lot of speech out there. It would be good if machine can actually extract information from that. And I tell always the students there is a job security. It's not going to be solved during your lifetime. Certainly not during mine. I mean, sort of if you get into it. In addition, I mean, I know that this is maybe on YouTube, but also if you don't like it, you can get fantastic jobs. There is half of the IBM group ended up on the Wall Street, making insane amount of money. So I mean, you know, what skills which you get in recognizing speech, working on speech, can be also applied in other areas. Obviously, it can be applied in vision and so on and so on. So speech has been produced to be perceived. Here is Roman Jakobson, great Harvard, MIT guy, passed away, unfortunately. He would be now 100 and something. He says, we speak in order to be heard, in order to be understood. Speech has been produced to be perceived. And over the millennia of the human evolution, it evolved this way so that it reflects properties of human hearing. And so I'm very much also with Josh, if you build up a machine which recognizes speech, you may be verifying some of the theories of speech perception. And I'll point out to that along the way. How do I know that the speech evolved to fit the hearing and not the other way around? I got some big people arguing over that because they say, you don't know, I mean, basically, but I know, I think. Well, I think that I know, right? Every single organ which is used for speech production is also used for something much more useful, like sort of typically eating and breathing. So this is the organs of speech production: lungs, the lips, teeth, right, nose, and velum, and so on and so on. Everything is being used for some life-sustaining functions, including speaking. So I know that you know, it's not the same in hearing. Hearing has evolved to hear, for hearing. Maybe there are some organs of balance and that sort of things, but mostly you do hearing. In speech, everything what is being used has been used for, is used for something else also. So clearly we just learn how to speak because we had the appropriate hardware there and we learn how to use it. So, in order to get the message, you use some cognitive aspects which I won't be talking much about. So you have to use the common language. You have to have some context of the conversation. You have to have some common set of priors, common experience, and so on and so on. But mainly what I will be talking about, you need the reliable signal which carries the message. Because the message is in the signal. It's also in your head, but the signal supports what is happening in your head. So, how much information is in speech signal? This is I have stolen, I believe, from George Miller, I think. So if you look at the Shannon's theory, I mean, there will be about 80 kilobits per second. And indeed, we can generate a reasonable signal without being very smart about it, just by coding it to 11 bits at 8 kilohertz per second, 88 kilobits per second, that verifies it. So this is how much information might be in the signal. How much is in the speech is actually sort of not very clear, but at least we can estimate it to some extent. If you sort of say, I would like to transcribe the signal in terms of the speech sounds, phonemes, so there is maybe about 40 to 49 phonemes or something, 41 phonemes. So if you look at the entropy of that, it comes to about 80 bits per second. So there is a 3 orders of magnitude difference. If you push it a little bit further, and indeed, I mean, if you speak with about 150,000 words, that means about 80 bits, 30 words per minute. Again, it comes to less than 100 bits. So, as I said, there's a number of ways how you can argue about this amount of information. If you start thinking about dependencies between phonemes, it can go as low as 10, 20 bits per second. No question that there is much more information in the signal than it is in a useful message which we would like to get out. And we'll get into that. Because what is in the message, there is not only information about the message, but there is a lot of other information. It's information about the health of the speaker, about which language the speaker is using, what emotions. There is who is speaking, speaker-dependent information, what is the mood, and so on and so on. And there is a lot of noise coming from around. Reverberations, we talk about it quite a lot in the morning, all kinds of other noises. So what I call noise in general, I call everything what we don't want besides the signal, which in speech recognition is the message. So when I talk about the noise, it can be information about who is speaking, about the emotions, about the fact that maybe my voice is going, and so on and so on. To my mind, purpose of perception is get the information which carries, get the signal which carries the desired information and suppress the noise, eliminate the noise. So the purpose of perception, being a little bit vulgar about it, is how to get rid of most of the information very quickly, because otherwise your brain would go bananas. So you basically want to focus on what you want to hear, and you want to ignore, if possible, everything else. And it's not, of course, easy, but we discussed that again in the morning about some techniques, how to go about it, and I will mention a few more techniques which we are working on. But this is a key thing, is purpose of perception is to get what you need and not to get what you don't need, because otherwise your brain would be too busy. Speech happens in many, I mean, very simple example, speech happens in many, many environments, and there is a lot of stuff happening around it. So the very simple example, which I actually used when I was giving a talk to some grandmothers in Czech Republic, is that what you can already use is that the fact that things happen at different levels, and they happen at different frequencies. Perception is selective. Every perceptual mode is selective and attends only to the part of the world. You know, we don't hear the radio, we don't see the radio waves, and we don't hear the ultrasound. And so does all the lower animals, and so on and so on. So there are different frequencies, different sound intensities, and in the first approximation, this is what you may use. If something is too weak, I don't care. If something has too high frequencies, I don't care, and so on and so on. There are also different spectral and temporal dynamics to speech, which we are learning about that quite a lot. it happens at different locations of the space. Again, that's the reason why we have a spatial directivity. That's why we have 2 ears. That's why we have a specifically shaped ears, and so on and so on. There are also other cognitive aspects. I mean, sort of like the selective attention. Again, we talk about it. The people appear to be able to modify the properties of your cognitive processing depending on what you want to listen to. And my friend Dima Mesgarani with Eddie Chang, who was supposed to be here instead of me, just had a major paper in Nature about that, and so on and so on. There's a number of ways how we can modify the selectivity. We talk about the sharpening the cochlear filters, right? I mean, depending on the signal from the brain. So speech happens like this. Start with the message. You have a linguistic code, maybe 50 bits per second. There is some motor control. Speech production comes to a speech signal, which has 3 orders of magnitude larger information content. Through speech perception and cognitive processes, we get somehow back to the linguistic code and extract the message. So this is an important, from the small low bit rate to high bit rate to the low bit rate. In production, actually, I don't want to pretend it happens in such a linear way. There are also feedbacks. So there is a feedback from, you listen to yourself when you are speaking. You can control how you speak, and you can also actually change the code because you realize, oh, I should have said it somehow differently. In speech perception, again, Josh talked about it. You can, if the message is not getting through, you may be able to tune the system in some ways. You may be changing the things, you know. And you may also use the very mechanical techniques, as I told you, close the window or walk away. There is also feedback through the dialogue. So from between message and message, depending on what I'm hearing, I may be asking for different kind of questions, so which also modifies the message of the sender. How do we produce speech? So we speak in order to be heard, in order to be understood. So very quickly, I want to go back to something which people already forgot a big way, which is Homer Dudley. He was a great researcher at Bell Laboratories before the Second World War. He retired, I think, sometimes early in the 50s. Passed away in the 60s. He was saying message is in the movements of the vocal tract which modulate the carrier. So message in the speech is not in fundamental frequency. It's not the way you are exciting your vocal tract. Message is how you shape the organs of speech production. Proof for that is that you can whisper and you can still understand. So it's how you excite the vocal tract is secondary. How do you generate this audible carrier is secondary. You can use the artificial larynx, right? So there is this idea, there's a message is being goes through modulator into carrier, comes out the speech. So this modulation actually has been used a long time ago, and excuse me for being maybe a little bit simplistic, but it's actually in some ways interesting. So this was the speech production mechanism which was developed in sometimes in the 18th century by the guy Johann Wolfgang Ritter von Kempelen, and he actually had it right. The only problem is nobody trusted him because he also invented mechanical Turk, which was playing the chess. And so he was caught as a cheater. So when he was showing his synthesizer, nobody believed him. But anyways, he was definitely a smart guy. So he used already the principle which is then now used. This is a linear model of speech production developed actually before the Second World War. Really, again, the laboratories should get the credit. I believe this is stolen from Dudley's paper. So there is a source, and you can change it to periodic signals or to random noise if you are producing voice signal or unvoiced signal. And then there is a resonance control which goes into amplifier and produces the speech. So this is a key here. This is a key to the point that Dudley developed what is called a voder. And he trained the lady who spent a year or something to play it. It was played like an organ. And she was changing the resonance properties of this system here. She was creating excitation by pushing on the pitch pedal and switching on the wrist bar, And if it works well, we may even be able to make the sound. This is a test.
Will you please make the voters say for our Eastern listeners, good evening, radio
This is a real
audience.
speech. This is.
And now for our Western listeners, say good afternoon, radio audience.
Good afternoon, radio audience.
Good enough, right? I mean, sort of. So already in 1940s, this was demonstrated at a trade fair. And the lady was trained so well that in the 50s, when Dudley was retiring, they brought her in. She was already retired a long time ago, and she still could play it. How the speech works, I mean, maybe, I wanted to jump this, but anyways, let's go very quickly through that. So this is a speech signal. This is an acoustic signal. Changes in, this is a sinusoid, high pressure, low pressure, high pressure, low pressure. If you put somewhere in the path some barrier, what happens is you generate a standing wave. A standing wave stands in a space, and there are high pressures, low pressures, high pressures, low pressures, but the frequency depends on the frequency. I mean, the size of this standing wave depends on the frequency of the signal. So if I put it into something like a vocal tract, which we have here, so this is a glottis, this is where it gets excited. This is a very simple model of vocal tract, and here I have a lips. So it takes a certain time to propagate through the tube, and the tube will have a maximum velocity at a certain point, so that it will be resonating at a quarter wavelength of the signal, 3/4 of the wavelength of the signals, in 5/4 of the wavelength of the signal, and so on, and so on. So we can compute at which frequencies this tube will be resonating. This is a very simplistic way of producing speech, but you can generate reasonable speech sounds with that. So if we start putting a constriction there somewhere, which emulates the way, very simple way how we can speak, by moving the tongue against the palate or making a constrictions in the speech. So when the tube is open like this, it resonates at 500, 1500, 2500 if the tube is 17 centimeters long, which is a typical length for the adult vocal tract. So if I put a constriction here, everything moves down, because there is such a thing like perturbation theory, which says that if you are putting a constriction to the point of the maximum velocity, which is of course at the opening, all the modes will go down. But as you go on, basically the whole thing keeps changing. The point is that almost in every position of the, say, this tongue, all the resonance frequencies are changing. So the whole spectrum is being affected. And it may become useful to explain something later. So we go like this. At the end, you end up again in the same frequencies. From these are called nomograms, and they will be heavily worked on at the speech group at MIT at Stockholm. So you can see how the formants are moving, and you can see it for every position of here we have a distance of the constriction from the lips. For every position, we are having all the formants moving. So information about what I'm doing with my vocal organs is actually at all frequencies, all audible frequencies, in different ways, but it's there everywhere. It's not a single frequency which would carry information about something. All the audible frequencies carry information about speech. That's important. You can also look at it and you can say, you know, what is where the front cavity resonates, or where the back cavity resonates. Again, this front cavity resonance may become interesting a little bit later if we get to that. But this is a very simplistic model of the speech production, but pretty much contains all the basic elements of the speech. Point here is that depending on the length of the vocal tract, even when you keep the constriction at the same position, this is how long is this front part before the constriction is. So all the resonances are moving, but shorter vocal tract, like a children vocal tract, or even a number of females, they typically have a shorter vocal tract than the males. There is a different number of resonances. So if somebody is telling you the information is in the 4 months of speech, question it. because it's actually impossible to generate the same speech being two different people, especially having two different lengths of the vocal tract. We get into it when we talk about the speaker dependencies. Second part of the equation is hearing. So we speak in order to be heard, in order to be understood. And again, thanks to Josh, he spent more than sufficient time explaining you enough what I wanted to say. I will just add some very, very small things. So just to summarize, Josh was telling you periphery works basically like a bank of bandpass filters with a changing frequency and output depending on sound level intensity. There are many caveats to that, but I mean, in the first approximation, I 100% agree this is enough for us to follow the rest of the talk. Second thing which Josh mentioned very briefly, but I want to stress it because it is important, firing rates, because you know that the cochlea communicates with the rest of the system through the firings, through the impulses. Firing rates on the auditory nerve of the order of 1 kilohertz every 1 millisecond. But as you go up and up in the system, already here on the colliculus it's maybe order of magnitude less, and in the level of auditory cortex is 2 orders of magnitude less. So of course, I mean, you know, this is how the brain works. I mean, so here we have from periphery up to cortex. But also, I think it was mentioned very briefly, if you look at it, number of neurons increase more than actually decrease in the firing rates. Because if we have, again, those are just orders of magnitude, right? 100,000 neurons maybe on level of auditory nerve or cochlear nucleus, and you have 100 million neurons maybe on the level of the brain. And it can become handy later when, if I get all the way to the end of the talk, I will recall this piece of information. Another thing which was mentioned a number of times is that there are not only connections from ear, from the periphery to the brain, but there is, by some estimates, many, many more. I mean, again, I mean, the estimates vary, but this is something which I have heard somewhere. Maybe there is maybe almost 10 times more connections going from brain to the ear than from the ear to the brain. And typically, the nature hardly ever builds anything without a reason. So there must be some reason for that, and perhaps we will get into that. Josh didn't talk much about the level of on the cortex. So what's happening on the lower levels on the periphery? They are just these simple increases on the firing rates. There is a certain enhancement of the changes. So at the beginning of the this is a tone, right? The beginning of the tone, there is a more firing on auditory nerve. At the end of the tone, there is some deflection. But when you look at the higher level of the cortex, all these wonderful curves, which are sort of increasing with the intensity like it would if you had a simple bandpass filter, start looking quite differently. So majority, what I heard, the majority of the cortical neurons are selective to certain levels. Basically, the firing increases to a certain level, and then it decreases again. And they are, of course, selective at different levels. Also, you don't see just these simple things like here that your firing starts as a tone starts, but they are neurons like that, but there are also neurons which just are interested at the beginning of the signal. There are neurons which are interested in beginning and ends. There are neurons which are interested only at the ends of the signals, and so on and so on. Receptive fields, again, it's been mentioned already before. They are just as we have a receptive fields in the visual cortex, we have also receptive fields in auditory cortex. Here we don't have here we have a frequency and a time, unlike X and Y receptive fields, which are typical sort of first thing you are hearing about when you talk about visual perception. They come in all kinds of colors. They tend to be quite long. Meaning they can be sensitive for about a quarter of the second. Not all of them, but certainly there are many, many different cortical receptive fields. So some people are suggesting, given the richness of the neurons in auditory cortex, it's a very legal thing to suggest that maybe the sounds are processing in following way. Not only that you do the frequency analysis in the cochlea, but then on the higher levels you are creating many pictures of the outside world. And then, of course, only the question is here, it ends up, this is Murray Sachs and people from Bell Labs, from Johns Hopkins in 1988. They just simply said pattern recognition. But I believe there is a mechanism which picks up the best streams and leaves out not so useful streams. But the concept was here around for a long time. So this was physiology 101. Psychophysics. Psychophysics is thing that you place the signals to listeners and you ask them what they hear. But we want to know what is the response of the organism to the incoming stimulus. So simply you play the stimulus and you ask what is the response. First thing which you can ask, do you hear something or not? And you already will discover some interesting stuff. Hearing is not equally sensitive everywhere. It's selective, and it's more sensitive in an area somewhere between 1 and 4 kilohertz. It's much less sensitive at the lower frequencies. This is a threshold. On the threshold level is yet another interesting thing. If you just apply the signals in different ears, as long as the signals happen within a certain period, about a couple of 100 milliseconds, and it's a couple of 100 milliseconds you hear from me more often, the thresholds are half. Basically, neither of these signals would be heard if you applied only single one, but if you apply both of them, basically you hear them. If you play the signals at different frequencies, if these signals are close enough, close so that, as Josh mentioned about the beats, they happen within one critical band, again, neither blue or green signal would be heard on its own, but if you play them together, you hear them. But if they are further in frequency, you don't hear them. Same thing is if these guys are further in time, you wouldn't hear them. So this subthreshold perception actually is kind of interesting, and we will use it. Which we didn't talk much about is that there are obvious ways how you can modify the threshold of hearing. Here we have a target, and since it is higher than the threshold of hearing, you hear it. But if you play another sound called masker, you will not hear it because your threshold basically is modified. It's called the masked threshold, and this part is suddenly not, this target is not heard. The target can be something useful, but in MP3 it can be pretty annoying because it's typically noise. You try to figure out how you can mask the noise by the useful signal. You're computing these masked thresholds on the fly. Initial experiment with this, what is called simultaneous masking, was following. And again, it was Bell Labs, and Fletcher and his people. They would figure out what is the threshold at a certain frequency without the noise. But then they would put noise around it, and the threshold had to go up because there was a noise, right? So it was, there was a masking. Then they made a broader noise, and threshold was going up, as you would expect. There was more noise, so you had to make the signal stronger. And you made, to a certain point, when you start making a band of noise too wide, suddenly it's not happening anymore. There is no more masking anymore. That's how they came with this concept of critical band. Critical band is what happens inside the critical band matters, basically influences the decoding of the signal within a critical band, but if it happens outside the critical band, it doesn't. So essentially, if the signals are far away in frequency, they don't interact with each other. And again, this is a useful thing for speech recognition people. They didn't much realize that that this is the main outcome of the masking. Critical bands, discussions are here, but this is a bark scale which has been developed in Germany by Zwicker and his colleagues. It's pretty much logarithmic from about 600-700 hertz up, and it's approximately constant up to 600-700 hertz. If you talk to Cambridge people, Brian Moore, and that sort of thing, they tell you it's pretty much logarithmic pretty much everywhere, but not really. But the critical bands, remember critical bands from the subthreshold things? Again, a critical band in masking. It's telling you if things happen within the critical band, they integrate. If they happen outside each of them outside the critical band, they don't interact. Another masking is temporal masking. So you have a signal, and of course, if you put a masker on it, it's a simultaneous masking. You have to make it signal much stronger in order for you to hear it. But it also influences things in time. This is called what is called forward masking, and this is the one which is probably more interesting and more useful. It's also backward masking when a masker happens after the signal, but it's probably has a different origin, more like cognitive rather than peripheral. So there is still a masker. You have to make the signal stronger. Up to a certain point, when the different distance between masker and the signal is more than 200 milliseconds, there's no masker anymore. Basically, there is no temporal masking anymore, but it is within this interval of 200 milliseconds. If you make mask stronger, masking is stronger initially, but it also decays faster, and again decays after about 200 milliseconds. And so whatever happens outside this critical interval, about a couple of hundred milliseconds, doesn't integrate, but if it happens inside this critical interval, that seems to be influencing, these signals seem to be influencing each other. And again, I mean, I talk about the subthreshold perception. If there were two tones which happen within 200 milliseconds, neither of them would be heard in isolation, but they are heard if you play them together. Another part which is kind of interesting is that loudness depends, of course, on the intensity of the sound, but it doesn't depend linearly on that. It depends with about cubic root. So if in order to make a signal twice as loud, you have to make it about 10 times more in intensity for stimuli which are longer than 200 milliseconds. Equal loudness curves. This is a threshold curve. But these equal loudness curves are telling you what the intensity of the sound, would need to be in order to hear it equally loud. So saying that if you have a 40 dB signal at 1 kilohertz and you want to make it equally loud at 100 hertz, you have to make it 60 dB, and so on. These curves become flatter and flatter, most pronounced at the threshold at lower levels, but they are there and they are actually kind of interesting and important. Hearing is rather nonlinear. Properties depend on the intensity. Speech, of course, happening somewhere around here where the hearing is most sensitive. That was the point here. Modulations, again, we didn't talk much about that, but modulations are very important. Since 1923, it's known that hearing is the most sensitive to certain rate of modulations around 4 or 5 hertz. These are again experiments from Bell Labs, repeated number of times. So this is for AM modulations. This experiment, what you do is that you modulate the signal and change the depth and change the frequency, and you are asking, do you hear the modulation or don't you hear the modulation? Very interesting. Interesting thing is if you look again, I mean, I refer to what Josh was telling you in the morning. If you just take one trajectory of the spectrum, you treat it as a time domain signal, remove the mean, and compute its Fourier components, frequency components. They peak somewhere around 4 hertz, just where the hearing is the most sensitive. And so hearing is not very sensitive, obviously, to when the signal is non-modulated, but also there are almost no components in the signal which would be non-modulated, because when I talk to you, I move the mouse, right? I mean, I change the things, and I change the things about 4 times a second, mainly. When it comes to speech, you can also compute music. You can also figure out what are the natural rhythms in the music. I stole this from, I believe, from the Munich group, from Fastel, Vico Fastel. He played 60 pieces of music, and he asked people to tap to the rhythm of the music. And this is the histogram of tapping. Most of the people, for most of the music, tapping was about 4 times a second. This is where the hearing is most sensitive, and this is the FM, I mean, the modulation frequency of this music. So people play music in such a way that we hear it well, that it basically resonates with the natural frequency of which we are perceiving. You can also ask the similar things in speech. You can play the speech sentences, and you ask people to tap into rhythm of the sentences. Of course, what gets out is the syllabic rate, and syllabic rate is about 4 Hertz. Where is the information in speech? Well, we know what the ear is doing. It analyzes signal into the individual frequency bands. We know what Homer Dudley was telling us. The message is in the modulations of these frequencies. As a matter of fact, that was the base of his vocoder. What he also did was that he designed, actually it wasn't only him, there was another technique. This one is kind of somehow cleaner, thing which is called a spectrograph, which tells you about the spectrum of frequency components of the acoustic signal. So you take the signal, you put it through a band of bandpass filters, and then here you basically display on the z-axis intensity in each frequency band. This was, I heard, used for listening for German submarines, because they wanted to, they knew that acoustic signatures were different for friendly submarines and enemy submarines. People listened to it for it, but also people realized that it may be useful to look at the signal, acoustic signal somehow. Waveform wasn't making all that much sense, but spectrogram was. Danger there was that people who were working in speech got hold of it. And then they start sort of looking at these spectrograms, and they say, we are seeing the information here. We are seeing the information in ways the spectrum is changing. Because not only that this was the way the original spectrogram was developed, that you are displaying changes in energy in individual frequency bands, but you can also look at it this way, and you get what is called short-term spectrum of speech. And people said, oh, this short-term spectrum looks different for R than for E, so maybe this is the way to recognize speech. So indeed, I mean, those are two ways of generating the spectrograms. I mean, this was the original one, band of bandpass filters, and you were displaying the energy as a function of time. This is what your ear is doing. That's what I'm saying. This is not what your ear is doing, that you take short segments of the signal and you compute the Fourier transform, and then you display the Fourier transform one frame after time. But this is the way most of the speech recognition systems work. And I'm suggesting that maybe we should think about other ways. So now we have to deal with all these problems. So we have a number of things coming in the form of the message with all this chunk around it, but machine recognition of speech would like to transcribe the code which carries the message. This is a typical example of the application of speech recognition. I'm not saying this is the only one. There are attempts to recognize just some keywords. There are attempts to actually generate the understanding of what people are saying and so on, but we would be happy in most cases just to transcribe the speech. Speech has been produced to be perceived. We already talked about it. It evolved over the millennia to fit the properties of hearing. So this is, I'm sort of seconding what Josh was saying. Josh was saying you can learn about hearing by synthesizing stuff. I'm saying you can learn about hearing by trying to recognize the stuff. So if you put something in and it works, and it supports some theory of hearing, you may be kind of reasonably confident that that was something which has been used for. Actually, it's a paper about that, which of course I'm a co-author, so I didn't want to show that. I thought I will delete this one, but I didn't do it at the last minute. Anyways, speech recognition. Speech signal high bit rate, recognizer comes in, information low bit rate. So what you are doing here, you are trying to reorganize your stuff. You are trying to reduce the entropy, right? If you are reducing the entropy, you better know what you are doing, because otherwise you get real garbage. I mean, that's kind of like one of these common sense things, right? So you want to use some knowledge, plenty of knowledge in this recognizer. Where does this knowledge come from? We keep discussing it all the time. It can come from textbooks, teachers, intuitions, beliefs, and so on. And it's a good thing about that you can hardwire this knowledge. And so you don't have to learn it, relearn it next time based on the data. Of course, problem is that this knowledge may be incomplete, irrelevant, can be plain wrong. Because, you know, who comes that whatever teachers tell you or textbooks tell you or your intuitions are or beliefs is always true. Much more often now, what people are using is that the knowledge comes directly from the data. Such a knowledge is relevant and unbiased, but the problem is that you need a lot of training data, and it's very hard to get architecture of the recognizer from the data. At least I don't know quite well how to do it yet. So these are two things. And again, I mean, let me go back to 50s. First, knowledge-based recognizer was based on the spectrograms. There was Richard Galt, and he was looking at the spectrograms and tried to figure out how the short-term spectrum looked like for different speech sounds. Then he thought he will make this finite state machine which will sort of generate the text. Needless to say, it didn't work too well. He got beaten by data-driven approach, where people took a high-pass filtered speech, low-pass filtered speech, displayed energies from these two channels at the time it was oscilloscope, and they tried to figure out what are the patterns. They tried to memorize the patterns, make the templates from the training data, and they tried to match it for the test data. It was recognized, which was recognized in 10 digits, and it was working reasonably well, better than 90% at the time, for a single speaker and so on and so on. But it's interesting that already in the 50s, the data-driven approach got beat by the knowledge-based approach, because knowledge maybe wasn't exactly what you needed to use. They were looking at the shapes of the short-term spectra, basically. Of course, now we are in 21st century, finally. A number of people say this is the royal way of recognizing speech. You take the signal as it comes through the microphone, you take the neural net, you put a lot of training data, which contain all sources of unwanted variability, basically all possible ways of you can disturb the speech, and comes out the speech message. The key thing is, I'm not saying that this is wrong, but I'm saying that maybe this is not the most efficient way of going about it, because in this case you would have to retrain the recognizer every time. It's a little bit like sort of, you know, if you look at the hearing system of the simple animals, this is a moth here. So here is this is changes in acoustic pressure to changes in a firing rate. It goes to very simple brain, very small one. You know, this is not the way the human hearing is working. Human hearing is much more complex. And again, Josh already told us a lot about it, so I won't spend much time. The point here is the human hearing is frequency selective. It goes through a number of levels. This is very much along the, of course, deepness and that sort of things. But still, there is a lot of structure there in a hearing system. So it makes at least some sense to me. If you want to do what people are doing more and more, and there will be a whole special session next week at the Interspeech on how to train the things directly from the data, probably you want to have highly structured neural net. You want to have a convolutive preprocessing, recursive structures, and so on, a long short-term memory. Yeah, here are some. All these things are being used, and I think this is the direction to go. But I still argue that maybe there is a better way to go about it. A better way to go about it is that you try first to do some preprocessing of the signal and derive some way of describing the signal more efficiently using the features and so on and so on. Here, you put all the knowledge which you possibly may want to you already have. This knowledge can be derived from some development data, but you don't want to use directly the speech signal every time you are using you don't want to retrain basically every time directly from the speech signal. You want to reserve your training data, the task-specific training data, to deal with the effects of the noise which you don't understand. This is where the machine learning comes. I'm not saying that this is not a part of machine learning, but I mean, there are two different things which you are going to do. I was just looking for some support. This one came from Stu Gilman from Brown University and his colleagues. Stu Gilman is a machine learning person, definitely, but he says, we feel that meat is in the features rather than in a machine learning, because they go overboard basically explaining that if you just rely on machine learning, sure, you have a neural net which can approximate just about any function, given that you have infinite amount of data and infinitely large neural net, and they say infinities are kind of not useful engineering concept. So they feel like that the representations actually are, I hope they still feel the same. I didn't talk to them now, but seems like that there is some support in this notion what I'm saying. But of course, problem with the features is following. Whatever you stripped on the features, this is a bottleneck. Whatever you decide that is not important is lost forever. You will never recover from it, right? Because I'm asking for feature extraction. I'm asking for this emulation of the human perception, which strips out a lot of information. But I still think that we need to do it if we want to design a useful engineering representations. The other problem, of course, is whatever you leave in, the noise, the information which is not relevant to your task, you will have to deal with it later. You will need to train your machine on that. So you want to be very, very careful. You are walking the thin line here, sort of, what is it that I should leave out? What is it that I should keep in? It's always safer to keep a little bit more in, obviously. but this is the goal which we have here. And I wanted to say features can be designed, use development data. But what I'm saying, use the development data, design your features, and use them. Don't use this development data anymore. We have a lot of data for designing a good features, and I think that, again, is happening in the field. Good. How the speech recognition was done in 20th century. This is what I know maybe the most. So we'll spend some time, but it's still done largely. There are some variants of this recognition is still done. You take the signal and you derive the features. In the first place, you derive what is called short-term features. So you take a short segments of the signal, about 10 to 20 milliseconds, and you derive some features from that. That was in 20th century. Now we are taking much longer segments, but we'll get into that. But you derive it with about 100 hertz sampling every 10 milliseconds. So you turn one-dimensional signal into two-dimensional signal. And here, typically, if the first step is the frequencies. So those maybe, imagine those are frequency vectors or something derived from frequency vectors. Melkepstrom or stuff like that. Those are just tricks, signal processing tricks which people use. But one-dimensional to two-dimensional. Next thing is you estimate the likelihoods of the sounds each 10 milliseconds. So here, imagine that here we have the different, say, speech sounds, maybe 41 phonemes, maybe 3,000 complex dependent phonemes, and so on. Depends on, but those are parts of speech which make some sense. And they come typically from phonetics theory, and we know that you can generate different words, putting phonemes together in different ways, and so on and so on. So suppose for the simplicity that there's 41 phonemes. And so if there is a red one, red means that posterior probability of the, actually we need the likelihoods rather than posteriors. So if we derive posteriors, we just divided it by priors to get the likelihoods. So meaning that this phoneme has a high likelihood and the white ones don't have a likelihood at this time. So next step is that you do the search on it. This is a painful part, and I won't be spending much time on that. I just want to give you some flavor of this. You try to find the best path through this lattice of the likelihoods. And if you are lucky, the best path then is going to represent your speech sounds. So then next thing is only that you look and transcribe to go from phonemic representation from into the lexical representation, basically, because you know there's typically one-to-one relations. Well, should be careful one-to-one, but there is a relation, known relation between phonemes and the transcription. So we know what has been said. So this is how the speech recognition is done. Talking about this part, I mean, here we have to deal with one major problem, which is, like, the speech doesn't come out this way. It doesn't come out as a sequences of individual speech sounds. But since I'm talking to you, I'm moving the mouse continuously. There is a sync that first I can make certain sounds longer, certain sounds shorter, and then I add some noise to it. But finally, because of what is called co-articulation, each target phonemes gets spread in time. So you get the mess. But people say, sometimes people like to say speech recognition, this is our biggest problem. I claim to say this is not the problem. It is a feature, and feature is important because it comes quite handy later. Hopefully, I will convince you about that. But what we get is a mess. So this is not easy to recognize, right? We have the co-articulations, we have speaker dependencies, noise from the environment, and so on and so on. So the way to deal with it is to recognize that different people may sound different, communication environment may differ, so the features will be dependent on a number of things, on environmental problems, on who is saying things, and so on. People say same things in different speeds. I can speak faster, I can speak slower, still the message is the same. So we use what is called the hidden Markov model, where you try to find such a sequence of the phonemes which optimizes the conditional probability of the model given the data. And models you generate on the fly as many models as possible, actually infinite number of models, but of course, again, you can't do it infinitely, so you do it in some smart ways. And this is being computed through modified Bayes rule. Modified is because, for one, I mean, you would need a prior probability of the signal and so on. We don't use that. But also, what we are doing, we are somehow arbitrarily scale the things which are called the language model, because this is a prior probability of the particular utterance. This is the likelihoods coming from the data. Combining these two things together and finding the best match, you get the output which best matches the things. Model parameters are typically derived from the training data. Problem is how to find the unknown utterance. We don't know what is the form of the model, and we don't know what is the data. So we are dealing with what is called the doubly stochastic model, hidden Markov model. Speech is a sequence of hidden states. You don't see these hidden states, and also you don't know what comes from any state. So it's somehow, so you don't know for sure in which state you are on, and you don't know for sure what comes out, but you know that, well, you assume that this is how the speech looks like. So here again I have a picture, a little bit. I apologize for being trivial about this, but imagine that you have a string of group of people. Some are female, some are male. They are groups of males, groups are females. And each of them says something, says hi, and you can measure something. This is, say, fundamental frequency. You get some measurement out of that, but you don't see them. But what you know is that they interleave. Basically, for a while there is a group of males, then it switches to the group of female, and then you stay for a while in a group of female, and so on and so on. So basically, and you know what is the probability of the fundamental frequency for males. Those are distributions. You know what is the fundamental frequency for females. You know what is the probability of the first group being male. Subsequently, you also know what is the probability of the Because to me, the features are very important. As I told you, you don't want to leave stuff in which you don't need, but you don't want to take out stuff which you may need. I told you that one important role of the perception is to eliminate some of the information, basically, just to. So you eliminate the irrelevant, focus on the relevant stuff. So this is where I feel the first properties of perception can come in very strongly. Because this is what emulates this basic process of the speech, of the extraction of information from acoustic signals. The fact about the hidden Markov models, that speech consists of the sequences of sounds and they can be produced with different speed and sort of things, is important. But here we can use a lot of our knowledge. So features which can be also designed based on the data, and what comes out is probably very relevant to speech perception. So this is my point: how you can use the your engineering to verify some theories of speech perception. We use largely nowadays the neural nets to derive the features. So how we do it is that we because we know that best set of features are posteriors of the classes, and if the classes which we want to recognize are speech sounds, maybe it's going to be useful. If you do the good job, actually you can do the reasonable study. So if you take a signal, you do some pre-processing, and I will be talking about this pre-processing quite a lot. But then it goes into neural net, nowadays deep neural net, and you estimate the posteriors of different speech sounds. And what comes out, whatever is red, is always the high posterior probability of the phoneme. So we have duet, re, nove, say. This is a sequence of Italian digits, and you can do the reasonable stuff. As a classes, you can use directly context-independent phonemes in this example, small number. You can use context-dependent phonemes, which I use quite a lot because they try to address this fact that if the phoneme is produced, it depends on what happened in the neighborhood, parts of context-dependent phonemes, and so on. This is, again, a little bit secondary. These posteriors can be directly used in Viterbi search. This is the search through this lattice of the likelihoods in recognition. And again, I mean, it's coming back. This has been NIPS 1990, but this is the way most of the speech recognizers work. This is the major way now how you do the speech recognition. There's another way, which is called bottleneck or tandem. We were involved in that too, which was the way to make the neural nets friendly to people who were used to old generative HMM models. Because you basically converted your outputs from the posteriors into some features which your generative GMM model would like. So what you decorrelated them, you sort of Gaussianized them so that they have a normal distribution, and use it as a features. But bottom line is, if you get the good posteriors, you get the good features. And we know how to use them. And this is pretty much the mainstream now.